Enzymes are going to lower the energy of the transition state. So their job is to lower the activation barrier. If you have your leprechaun and there's a pot of gold at the other side of the rainbow, but it has to get up the top of the rainbow in order to get to the pot of gold. Even if it would be much, much happier with that pot of gold, even if it's more thermodynamically favorable to be at that pot of gold, you have to get over the top of the rainbow. And if that rainbow is really, really tall, it's going to be hard to do that. So what an enzyme is going to do is it's going to lower the height of that rainbow. It's going to lower the energy of the activation barrier and allow the leprechaun to get to the other side. But when you're at the top of the rainbow, you can go either way. And so enzymes are going to catalyze the reaction in both directions. Remember that we can also kind of more formally talk about that transition state and the activation energy. We represent the transition state with like this double dagger symbol, and the energy taken to get to that transition state, the activation energy, we represent it with this delta G double dagger. So remember that the overall delta G is going to be the difference between the energy of your substrate and the energy of your products. But then what can vary, that's not going to change, but what can vary is the path in between them. And the height of the tallest peak, the highest transition state, that energy required to get to that delta G double dagger for that highest energy transition state, that's going to be our rate determining step. And so if an enzyme wants to speed up the rate at which an enzyme reaction happens, it's going to need to lower that activation barrier. And we saw how one of the key ways that enzymes could do this was by providing lots of favorable interactions to the transition state. So we remember we wouldn't want it to bind too tightly to the substrate, because then we're kind of digging ourselves a deeper hole that leprechaun has to go climb out of. But if we lower the transition state, if we provide these favorable binding interactions to the transition state, well, now we're able to lower the activation barrier, allow us to get to the other side more easily. So for example, if we had a nucleophilic addition and elimination to a carbonyl group, which we're going to see over and over and over again, what we would see is that basically we have a nucleophile. Remember, often a nucleophile is going to be a lone pair and an oxygen or a nitrogen, and our electrophile is often going to be a carbonyl carbon. We draw our arrow from our nucleophile to the electrophile. So in this case, our nucleophile is going to be the oxygen on this water, and our electrophile is going to be this carbonyl carbon. When we have them attack, basically what's going to happen is ultimately we're going to form a tetrahedral intermediate. So an intermediate, we have actual bonds here, but in order to get that to that point, we first had to have a partial bond being formed and this partial bond being broken. So this is our transition states. This is what we put in brackets with the double dagger. This is what the enzyme is going to be the most stabilizing to and provide the most help for. Additionally, we would also have another transition state on this side of the intermediate as we go from having these bonds formed to then breaking off this other bond. In this example, they're only showing the transition state, this transition state, because this is going to be the slower one, the rate determining step. But you are also going to have a transition state on the other side, and so you're going to have two peaks on either side of that valley, representing where the valley is your intermediate, and the peaks on either side are going to be your transition states. But in order to even get to this transition state, we have to make it more likely. And so we can do this in a couple of ways. And so we're going to look at how acid and base catalysis can either strengthen the nucleophile or strengthen the electrophile, and how other things like metals can help stabilize the charge on the transition state. And all these enzymes can kind of all provide interactions with this transition state that are going to help lower the energy required to actually get there. And then once it gets there, which way it goes is going to depend on the overall thermodynamic favorability of the reaction, which is something that enzyme can't change. But by doing it in little steps where each step isn't quite as bad, it can do things like make it easier for the reaction to happen. And kind of controlling the concentrations of the products and the reactants, we can favor one direction or the other. Enzymes can use a variety of different strategies to make reactions happen, and different enzymes can catalyze the same reaction in different ways or catalyze different reactions in the same way. All the enzymes are going to do proximity catalysis. This is also known as entropy reduction. Basically, they just bring things together. They make it easier for them to react. They hold them in the right position to react. With acid-base catalysis, here what you're doing is you're actually going to be giving or taking protons, and this is going to help make molecules more reactive so that they are going to react. We'll see this a lot when we have like nucleophilic reactions. We'll see metal catalysis. Metals are great. They can serve as these kind of like coordination hubs, hold on to multiple things. They've also got that positive charge that's great for holding a negative charge and helping stabilize negatively charged transition states. We'll also see examples of covalent catalysis where the enzyme is actually making a temporary link with the substrate. So instead of just giving or taking protons from it or something, it's actually getting stuck on it. So it's like you go when you try to cut something and your scissors get stuck on your paper, and then you finally get the paper off. So that would be like a covalent catalysis. Although there's a lot of different enzymes and the mechanisms can look pretty complicated, it's the same main things that come up over and over again. We'll also look at a little more complicated things when we're dealing with redox and stuff. But bottom line, these are the key ones. Keep your eye on them.